Okay, so today I'm going to talk about the twin paradox. So let me review first. Remember, we now have these Lorentz transformations. They took the placement of the Galilean transformations. Remember, these are from Frank to Mary, Mary to Frank. And these always give you the speed of light as the speed of light. And the transformation graphically would be a point on this black coordinate system transforming it to the red coordinate system. Those are the equations. Remember, we had this gamma factor, and this is the plot of it. If you're going slow, it's 1, and then it has an asymptote. The important thing to remember is that when we're going at 86% the speed of light, this factor is 2 right here. So we like that a lot. And then when one of them was at the proper time, remember, proper time is you measure both events at the same location, right here. The person who isn't on the proper time always gets a larger time, which means he's going to see the other clock running slow. Right? It works both ways. It's symmetric. Same with the length. We also have a proper length is always the longer one right here. So a moving meter stick shrinks by this amount right here. The proper length is the one that's not moving relative to you. Okay, so today I'm going to talk about the twin paradox. So let me just write this c squared t prime squared minus x prime squared. Let me look at that quantity and let me transport that into the unprimes right here. So if we do that, I'm just going to take the t prime, we have c squared, and then I'm just going to put in what t prime is. Remember, t prime is right there, so I'm just going to plug in that transformation. So we have t minus xv all over c squared all over the square root of 1 minus v squared over c squared minus x prime squared minus, and then we'll take our x prime, which is right here, and square it. X minus vt all over the square root of 1 minus v squared over c squared squared. Okay, so let's just simplify that a little bit. We notice that they have a common denominator without the square root because we're squaring it. So we got a 1 minus v squared over c squared. And then hopefully we can square all this out in the numerator. You notice this first term is t squared times c squared. So we have c squared t squared. Okay, and then the second term, we have 2 times the first times the second. So that would be 2, and it'd be a minus 2. The first, which is t, times the second, which is xv over c squared, but I'm multiplying it by c squared, so it's xv. The c squareds drop out. And then we have the second term right there, which is plus x squared v squared over c to the fourth, but times c squared just gives me over c squared. Okay, we keep going here. Then over here, we have minus x squared. And then the cross term is going to be minus, but I have another minus, so it's plus 2 times the first times the second. And then the last term is the last term squared. This one is plus v and v squared t squared, and then we have a minus right there. So it's minus v squared t squared. Okay, so there is, now if you notice we can cancel at least that term with that term right there. So we can simplify it a little bit. So now what I'm going to do is I'm going to combine the t squared terms. Actually, yeah, I'll combine the t squared terms, t squared. And what do I have? I have c squared minus v squared. And then I'll combine the x squared. I'll factor that out of these two terms. I'll factor out the minus x squared. So this term is 1. This term is going to be minus since I'm pulling out the minus. So it's minus v squared over c squared. And then we still have that denominator, which is 1 minus v squared over c squared. Okay, so there's that so far. And then this, I'm going to pull out the c squared. So I'm going to make this v squared over c squared when I pull out the c squared. So we got c squared, t squared, 1 minus v squared over c squared, minus x squared, 1 minus v squared over c squared, divided by 1 minus v squared over c squared. Okay, well, there's a 1 minus v squared over c squared in all three of these terms. I can cancel them all out. And so this becomes just c squared t squared minus x squared. Oh, that's kind of strange. We started with this. We ended with this, which is the exact same equation. We finally found something that is invariant to both Frank and Mary. They both agree on their ct squared minus x squared. Matter of fact, we can even put that over here as there's a nice new equation right here, that whatever c squared t squared minus x squared is, in Frank's frame, it's the same quantity in Mary's frame, c squared t prime squared minus x prime squared. We like things that are the same in all frames right here. Well, what does this mean right here? Well, let's go back to our picture. We have our picture right here. This was our x. This is our ct, just like we have up there. We also have our x prime. Maybe I'll do it in blue right here. So we've got this. There's our x prime. And then coming down this way, we have our ct prime. Okay, so now if we look at a point here, say this point right here, this point, this distance across here, Frank would say, oh, that's x away, right? Because these are different values of x on the black coordinate system. So that's x. And this distance up to here is ct. So this distance here is ct, right there. Well, suppose we look at the blue coordinate system right here. So this point right here in Frank's coordinate system is xct. What is that point in Mary's, in the blue coordinate system? What is that point? Well, what's x prime here? Well, you notice right here, this is the y-axis. This is x equals 0. So x goes out this way. Likewise, this is x prime equals 0. This is Mary's right at her origin right here. So this is 0 for x prime, ct prime. Okay. So if we just apply this rule we just made up, we just said that c squared t squared minus x squared, we'll start with this one down here, minus x squared is the same thing in Mary's frame, which is ct prime squared, c squared ct prime squared minus her x prime squared, but her x prime is 0. So this is what we have right here. That must be true right there. Well, where is ct prime? Ct prime is right here. So ct prime is from here to here. You notice we have a triangle right here. Normally, when you work with triangles, you have Pythagorean's theorem, and you say that this squared plus this squared equals that squared. But you notice we don't have that. Pythagorean's doesn't work. If you look at this equation right here, this is shorter than this because this ct prime, c squared t prime squared, is c squared t squared minus some stuff. So on this triangle, this length is shorter than that length right here, which is very strange right there. How can that length be shorter than this length? Well, it's because it's not real space. This is for special relativity. So this diagonal is actually smaller than this. And it looks like the bigger the x is, the shorter this length gets, which is really quite strange right here. Which means the faster you go through space, that is, if this is a lot bigger and you come way out here, the faster you go through space, the slower you go through time, right here. So it looks like your speed through space plus your speed through time is the speed of light, but if you go through space faster, your speed through time is less, right here. Okay, so we can use this to maybe figure out this twin paradox. So let's say that Frank and Mary are twins. So we'll just say they're twins right here. And Mary is going to leave. She's going to go to a star right here. So let me draw this diagram right here. Again. So here's x, here is ct. So Mary's going to go to a star, let's say 8 light years away. So here she is right here. She's going to go out to this star. And this star is 8 light years out to there. And she's going to go at a nice constant speed. We'll make the math easy. Her velocity will be 0.8 c. Right there. Okay, and so now if we just draw Mary's line, remember she's just heading up diagonally. Well, I guess we could have done this. She's just heading up diagonally right there. And we know how far out she goes. From Frank's point of view, this distance all the way out to here is 8 light years. So this is 8 light years. So there's your x right here. Well, and we also know this right here. How long is it going to take Mary to go 8 light years if she goes at 0.8 c? Well, again, we know speed is distance over time, or what do we want to calculate? We want to get the time. The time is equal to the distance over the speed. Well, the distance is 8 light years, and the velocity is 0.8 c. 8 over 0.8 is 10. Frank's going to say it took 10 years to get there, but that's the t, so it'd really be c times 10. 10c. We'll just call it 10 times c. Okay, and if we wanted to get the slope of this line right here, remember how I don't know if we need it, but we'll calculate it anyway. The slope is just the rise over the run. The rise is 10c. The rise is 10c. Over the run, well, 8 light years is really 8c because it's a light year. So this is really 8c, which is 10/8 or 1.25. So the slope here is 1.25. I don't know if we need it. Remember, her slope is always bigger than 1. It's really her c over her v. Okay, and then once she gets there, she says, I'm going to come back. Well, if she comes back, she should just follow come back this way right here. So then she's just going to head on back this way and get back to where Frank is, right there. Now her slope here will be the same but negative. It'd be negative 1.25. But this would take another 10 years for her return, 10c. Okay, but it would take 10 years. The time would be... So Frank would say, I'll see you in 20 years. It's going to take you 10 years to get there, 10 years to get back. Frank says, see you in 20 years. See you in 20 years. In 20 years. Okay, so he's just going to wait 20 years. Okay, now what is Mary? Now we'll look at Mary's Mary going up this way. Well, we already know we have this rule here, right there, that this length right here, this c squared t prime squared, let's just write that down, c squared t prime squared should equal this squared, well it's just this squared, 10 squared c squared, that's 100 c squared, minus x squared, which is 8. Remember, this is really 8c because it's light years. 8c, which is squared, which is 64c squared. So we can cancel all the c's out. 100 minus 64 is 36. Take the square root. So Mary would say, no, it's only going to take me, what, 6 years. Remember, this is a shortened one. This is only going to be 6 years, or CT would be 6C right here. But we'll just say the time here is 6 years. So she's going to say it took 6 years to get out, 6 years to come back in. Mary says, I'll see you in 12 years. So Mary says, see you in 12 years. See you in 12 years. Well, which one's right? They're both right. When she returns, when she returns, Mary will be 12 years older. Frank will be 20 years older. So they're not going to be, I don't know if you can still call them twins anymore, but there's going to be an 8-year age gap now between the two. Does that mean if you go out far enough, you could come back before you were born? No, you're always going forwards in time. It's just that you're going forwards in time at a different rate right here. And the further this goes out, the bigger the time difference would be right here. Now, you might say, how about what happened to all this symmetry we had? We said that everything was symmetric. You can't tell who's moving because relative to Mary, what does Mary see? She sees her not moving and she sees Frank on the Earth. The Earth is now a spaceship going out and coming back. So how come they didn't agree on when they came back right here? Well, the whole problem stems from, remember, all of this stuff we've been doing is called special relativity. Special relativity is the special case where you're going at constant speed, not accelerating. Well, she wasn't accelerating. That's a constant slope. That's a constant slope. But you notice right here, she went from this to that. That's an acceleration right here. Frank never had to do that right here. And that's what broke the symmetry right here. Now, we should really do this with general relativity. You remember, I said general relativity is not the special case of constant speed. It's the case where you're actually accelerating right here and you're moving around. That would be general relativity. We're not going over it, but it was just due to this little tilt right here that caused all the difference right there. Okay, so there's the twin paradox right there. No, it's not really a paradox, it's just that one of them accelerated, one of them didn't. Well, let's come back to this right here for a minute. You notice this is really my y-axis, and this is really my x-axis. And so if I just, call this just y for a minute. If we just call that y squared minus x squared, and that should equal y prime squared minus x prime squared, y prime squared minus x prime squared, which means this is a constant. Constant. For all observers, constant. I could give it any constant I want. Let's just call it 1 right here. So let's just say we have y squared minus x squared equals 1. Remember, this is really c squared t squared minus x squared equals 1. Well, what kind of an equation is this? Y squared minus x squared equals 1. Right here. Well, this is actually the equation of, it's not a circle. Y squared plus x squared equals 1 is a circle. Y squared minus x squared is a hyperbola. Hyperbola. And you might say, what does that look like when you plotted out a hyperbola? Well, it kind of looked like it had an asymptote, if you remember from math, at 45 and 45, and it was kind of a, it was kind of looking like this. It went something like that. Well, I'm just going to draw this, just this first quadrant for a minute right here. I don't care about the rest. And I did that over here. I just drew the first quadrant right there and there. So this thing keeps going down and it goes up like that. There'd be one over here too, but I don't. And so again, we have, here's my x and my ct, and here's the Mary's frame, x prime, ct prime right here. And we already said that, I don't know if I should use, well, let's stick with this. We got c squared t squared minus x squared equals, well, we're going to use 1 now, because there's my y, equals 1. And we also have c squared t prime squared minus x prime squared equals 1. Well, you notice this distance from here to here, this is where ct equals 0. Everywhere along this path, ct equals 0. If ct equals 0 right here, then actually, instead of even making it 1, why don't we make it minus? I can make it any constant I want. I'll just make it minus 1 right here. It's the same thing right there. If I make it minus 1, then if this is 0, x minus x squared equals minus 1. That means x equals 1. So this distance is 1 from here to here. Well, what about on this axis right here? Well, along this axis right here, t prime is 0 everywhere along here. Just like t was 0 here, t prime is 0 everywhere along here because you're right on the x-axis. So if this is 0, then x prime equals 1. So that means that this distance right there is also 1. So this distance here is also 1. Matter of fact, you put any axis. If this were another, let's say this is the axis, then that would be 1 unit. This is 1 unit in Frank's frame. This is 1 unit in Mary's frame. This would be 1 unit in Stan Speedy's frame, and so on right here. So those would be equal units right there. Equal 1 units, even though they don't look the same, but this would be 1 unit. Mary would say that's 1 unit. Suppose we wanted to get the slope of, say, this line right here. What is the slope of that? Right there. Well, normally the slope is what? dy dx. Slope is dy dx right there, where y is ct. Well, since we have this equation, how do we find dy dx? Don't you just take the derivative of this equation with respect to x? If we take the derivative of that with respect to x, we get 2y dy dx. So we got 2y dy dx minus 2x dx, which is 1, minus 2x dx equals, and the derivative of that is 0. Well, we can cancel the 2's and we can solve for dy dx. dy dx is equal to, put that on the other side, it's x over y. X over, remember what my y was, it was ct. So this is the slope, but I want to know what is the time right there. How do I know what t is? I know what t prime is. T prime is 0 there, but what is t? Well, remember we had our transformation equations right here. When t prime is 0, that means that the numerator is 0, which means t is just xv over c squared. So let's just replace our t with xv over c squared. So this is xv over c squared. The x's drop out, the c's drop, one of the c's drop out, and this becomes c over v. So the slope of this is the same as the slope of this, which was c over v. Remember we said the slope of this is c over v. So this red line and that blue line are parallel to each other. Well, you notice now, and same with this. This black line and this black line are parallel, but we can already see that. So on any axes you have out here, the slope of that line will be the same as the slope of your CT line right there. So let's just follow this down right here. Remember, since this line right here is parallel to this line, that means they all have the same x values. The x value there is the same as the x value there. Well, the x value there was 1, so this value on this red line is 1. You notice how this is shorter than that. That's why lengths shrink up. This is shorter than that. This is less than 1. And we could go back, since it's symmetric, if we take this line and follow it, and you notice right here, this is 1 unit, so this must be 1 unit right there, but you notice this is smaller than that line right there. So they each see each other's shorter right here. And we get it just from this hyperbolic space. That's what it's really due to right there. Now, one last thing here. I notice on one of your homework problems, the very last one, I think I can eliminate this. The very last problem on your first homework assignment, we had a rotation right here. We had 2 coordinate systems. We had a coordinate system that looked like this, x, y, and then we had a rotated coordinate system, which was x prime, y prime, where this thing was going around this way. So this is different than what we're doing. Here, it's all going this way. Our special relativity, they both come towards each other, but this is just a straight rotation, theta and theta. And we had a point out there on the black coordinate system. It was xy. And on the purple coordinate system, it was x prime, y prime, just like what we're doing over here, x prime, y prime. And I asked you to find the transformation equations. Now, you could have done it very easily just by looking at some of these triangles that you have on here. And you could have found it quite easily, but I have an easier way we can do it. We know that x prime is some function of x and y. So it's equal to something x plus or minus, actually we could say plus or minus something x plus or minus something y. Some trig function, since we have thetas in there, and we can do the same thing with y prime. It's plus or minus something x plus or minus something y. Maybe I'll put the x's first and then the something rather than afterwards. Plus or minus x something, and same with the y's. Y something, y something. Okay, now we do know that when theta is 0, they agree with each other. That is, x, if theta equals 0, we know that x prime equals x, and we know that y prime equals y. They know they agree because you're right on top of each other. Well, that must mean that this guy must be a cosine theta, because that way they'd both be equal, because cosine of 0 is 1. So this is going to have to be a cosine theta. And this one shouldn't be, it should be 0, so it better be sine theta, because we know sine of 0 is 0. So we'll make that sine of theta. Likewise, y is equal to y prime, so that better be a cosine theta over there. And this better be the sine theta. So, and now all we have to do is worry about the sine right here. Well, we can see that if we rotate let's put the point right here. If we rotate it by 90 degrees, you notice the x, if theta equals 90 degrees, then this x value goes up to here, which is to the y value. So x goes to y, and the value that was there, this point, y, goes over to here, which is minus x. Y goes to minus x. So if we come over to here and plug in 90 degrees, if you plug in 90 degrees, well, this guy's gone right here, so let's get rid of that. These guys, they're just keeping both plus. And then what do we say? When you're at 90 degrees, this one goes to 1, but x prime just goes to plus y, so that's just going to be a plus. And y prime went to minus x, so this one is just a minus right here. So, but you could have done it with trig right here. So these were the transformation for this equation right there. And if you went back the other way, you could just solve for x and y in terms of this, or you could just do it the way I just did it right here. Or you could just replace theta with minus theta and change the signs, just like we did. We changed the prime with the n prime, we changed the sign of the v. We could change the primes and the n primes and change the signs of the theta right here. But now, what do we have over there? Over there, we have something that looks similar to this right here, except it's with a trig function, because we know that this x squared plus y squared equals 1 gives you the circle, but now we know we have the hyperbola. So what we can do over there, we're not going to use it, but I just wanted to write it down. We could write the same thing here. We could say x prime is equal to x. Instead of the cosine, we could have put the cosh. X cosh. Let's just call it w for a minute, minus the ct, because we instead of y it's ct, sinh w, and we could have done the same thing. Ct prime is equal to minus x sinh w plus ct cosh w. So it's very similar to a rotation, but it's, remember, coshes and cinches are really cosines and sines of complex angles right here. And well, you might say, what is cosh w and what is sinh w? Well, cosh w was just 1 all over the square root of 1 minus v squared over c squared. And sinh w is actually just v over c divided by the square root of 1 minus v squared over c squared. And this squared minus this squared better be equal 1. Let's just see if it is equal to 1 right here. Because cosh squared of w minus sinh squared of w, that's going to be this squared, which is, you notice we're just going to get without the square root on the bottom, so you're just going to get 1 over 1 minus v squared over c squared, minus And then you square this, that's v squared over c squared all over 1 minus v squared over c squared. And you could combine these two together and you get 1 minus v squared over c squared over 1 minus v squared over c squared, which is 1. So we could have done it like this. Sometimes people do it that way, but we're just going to stick with our old v's and c's right here. Okay, just wanted to go over this.